Usually when we talk about a complex logistical problem, there's this expectation that if you just stare at it long enough, you can brute force a solution.
Right, like it's just a matter of enough time and caffeine.
Exactly. I mean, think about packing the trunk of a car for a vacation. You move the cooler, you shove the suitcase to the left, and eventually it just fits.
Yeah, because it's a manageable puzzle. You can actually see all the edges.
Right. But then you step into the world of modern network optimization, and suddenly that trunk you're trying to pack is like the size of a city.
Oh, at least. And you're trying to fit a million suitcases into it at the exact same time,
While following a rule book that is, 10,000 pages long.
which is pretty much the textbook definition of a combinatorial explosion. The number of possible configurations just grows so fast that it outpaces the computing power of the entire universe.
And that is exactly what we're getting into today. Welcome to this deep dive. Today, our mission is to uncover the hidden mathematical engine that solves these impossibly complex routing problems.
Yeah, it's fascinating stuff.
We're talking about everything from the GPS in your car calculating the fastest route home in real time, all the way down to the microscopic wiring inside your smartphone's processor.
Because it's all connected by the exact same underlying logic, which is honestly what makes this specific framework so incredibly powerful.
Right, and we're pulling all of this from an incredibly detailed 2026 presentation by a researcher who goes by the handle Lux036. The presentation is titled Network Optimization Theory, Algorithms, and EDA Applications.
It's a gold mine of a document.
It really is. Okay, let's unpack this because I want you to imagine you are planning the ultimate road trip.
Okay, I'm listening.
You need the absolute shortest route. You want to buy the cheapest gas along the way, and you absolutely must visit 3 specific friends in 3 different cities.
That sounds like a nightmare to plan.
Right. The sheer number of variables there is just completely overwhelming to calculate manually.
Oh, completely. I mean, if you try to calculate every single possible combination of routes and gas prices and stop sequentially, the sun would literally burn out before your computer finished the math.
Wow.
But mathematicians have essentially found a cheat code for these puzzles. They don't brute force the puzzle at all. They translate the puzzle into a completely different language.
The language of network flow.
Exactly, the language of network flow.
So before we can actually solve the puzzle, we have to understand the language of the map itself. And our source points out that these networks are, well, they're literally everywhere.
Yeah, they govern VLSI, which is the circuitry in all our electronics, but also the routing of the global internet, social network influence, even biology,
Wait, biology? Like how?
like metabolic pathways in your cells. Because
Okay.
at their core, all of those systems are just nodes connected by edges.
Oh, I see. Like intersections connected by roads. Or, servers connected by fiber optic cables.
Precisely. And the presentation highlights that one of the most foundational problems in these networks is something called the shortest path problem.
Which, I mean, sounds incredibly simple on the surface, right? Finding the quickest way from point A to point B.
Right. And algorithms like Bellman-Ford have been doing this for decades, but the mechanism behind Bellman-Ford is what actually makes it special.
Because it relies on iterative relaxation.
Yeah, exactly. It scans every single edge in the network and continually asks, hey, can I find a cheaper path to this node? And what's really powerful is that it can handle what they call negative weights.
Wait, I need to pause you there. How can a path have a negative weight? I mean, if a road is 50 miles long, the cost is 50 miles. You can't have negative 50 miles.
Right, it sounds impossible, but think about it less like distance and more like net resources.
Right.
Imagine you're driving an electric vehicle over a mountain pass. Driving up the mountain costs you energy, so that's a positive weight. But driving down the other side uses regenerative braking to actually charge your battery.
Oh, wow. So that downhill stretch effectively gives you a refund on your energy.
Exactly. That is a negative weight. Bellman-Ford actually accounts for those refunds, and by doing so, it can detect something incredibly important called negative cycles.
Negative cycles.
Yeah, if the algorithm keeps iterating and the total cost keeps dropping into infinity because it found a loop that just keeps generating a refund, it flags a negative cycle.
We are definitely going to come back to those negative cycles in a minute because they seem to be like the key to everything. Yeah. But to really grasp how mathematicians manipulate these networks, the source dives into flow and potential duality.
Specifically through Teligens's theorem.
Right. And the presentation says Teligens's theorem proves flow and tension are orthogonal. Now, For anyone who isn't a mathematician, orthogonal usually just means perpendicular, right?
Yeah, in geometry, sure.
So what does it actually mean in the context of a network?
It's basically the mathematical version of the conservation of energy. Let's visualize the network as a system of water pipes.
Okay, I can picture that.
Flow is the actual volume of water moving through the pipes, the edge flow. Potential is the water pressure at the joints or the nodes, pushing that water along.
Makes sense.
So, Tellegen's theorem states that if you take the flow along every single pipe and multiply it by the pressure drop across that pipe, the sum for the entire network will always be exactly zero.
Oh, I see. So the energy doesn't just vanish. Whatever pressure is lost pushing the water through a pipe is perfectly accounted for by the movement of the water itself.
Exactly. The movement and the pressure are perfectly complementary forces. When you solve for the flow, the mathematics inherently define the pressure.
You literally can't change one without the other reacting in a perfectly predictable way.
Right.
And here is where the presentation just completely blew my mind. It points out that there are these massive combinatorial problems that seem inherently hard. Things like bipartite matching.
Which is like assigning 100 different workers to 100 different specialized tasks.
Right. Or the assignment problem. And if you try to brute force them, they take forever. But if you formulate them as a network flow problem, suddenly they become quickly solvable in what they call polynomial time, or just P.
Yeah, it's amazing. And the reason that works is because the physical structure of a network naturally restricts the search space.
Wait, so you're telling me that matching people to jobs or routing internet traffic relies on the exact same math as water pressure in a pipe?
I am. Because when you translate a chaotic list of variables into a network of nodes, edges, cycles, and cuts, you are basically imposing physical laws onto abstract data.
The laws of flow and potential act as guardrails.
Exactly. You no longer have to search every impossible combination because the network structure literally prevents impossible combinations from existing in the math.
It turns the chaos into order. It takes a problem that would take a million years to solve and makes it solvable in seconds just by changing how we look at it.
It's a complete paradigm shift.
So now that we know translating these problems into flow makes them solvable, what is the actual mechanism doing the heavy lifting?
The engine driving all of this is a universal mathematical primitive known as NCF, or negative cycle finding.
The source calls this the universal primitive because it powers everything. Shortest paths, cycle canceling, parametric search. And the champion method for finding these cycles is something called Howard's algorithm.
Howard's algorithm is brilliant. It approaches the network using policy iteration. Instead of starting from scratch and mapping every single route, it makes an educated guess.
A policy.
Right, a policy about the best routing for the whole network. Then it evaluates that guess by hunting for negative cycles to improve it.
And it's also generator-based, meaning it doesn't need a single starting node to push flow from. It optimizes the network globally, all at once.
Yes.
Okay, here's where it gets really interesting. When I was reading about negative cycle finding, it reminded me of finding a glitch in a video game economy.
Oh, that's a great analogy.
Imagine you're playing an RPG, and you find out that if you buy a sword for 10 gold, trade it to a merchant for a shield, and then melt the shield down for iron, you can sell that iron for 12 gold.
You just made a profit of 2 gold.
Exactly. That loop is a negative cost cycle. The cost to you is literally less than zero. You are getting paid to make that loop. So what do?
You just keep looping that trade over and over.
Over and over, until the game developers patch the glitch.
And cycle canceling operates on that exact same logic. In min-cost flow, or MCF, the algorithm hunts down these glitches in the network.
So it's looking for those profits.
Yes.
Oh.
If trading flow along a certain path results in a net negative cost, meaning it makes the whole system more efficient, the algorithm pushes as much flow through that cycle as physical capacity allows.
Until the capacity is maxed out and the cycle disappears.
Right, it cancels the cycle, then it moves to the next glitch and the next, until there are absolutely no negative cycles left anywhere in the system.
Leaving you with the mathematically perfect absolute minimum cost state, just constantly exploiting inefficiencies until perfection is reached.
Exactly. And the source explains how this NCF engine scales up. It solves parametric problems like minimum cycle ratio, which is used for optimizing the clock periods in electronics.
But it doesn't just stop at simple linear problems where costs are fixed, does it?
Not at all. The hierarchy of what NCF can solve scales up dramatically. It starts at linear min cost flow, which we just discussed, but then it scales to convex min cost flow.
Convex meaning the cost change.
Right. In a convex problem, costs aren't fixed straight lines. The more flow you push through a pipe, the steeper the cost becomes, like traffic getting exponentially worse as a highway fills out.
Oh, sure.
NCF adapts to this by using gradients and line searches to find the bottom of that cost curve.
And it goes even further to quasi-convex and finally to fully constrained min cost flow using something called barrier methods. Okay, I have to push back here. What exactly is a barrier method? It sounds like we are building walls inside the math.
That is actually a really great way to picture it. In highly constrained systems, there are certain thresholds you absolutely cannot cross, or the system breaks.
Like physical limits.
Yes. A barrier method is a mathematical penalty function added to the algorithm. As the flow approaches a forbidden boundary, like a hard constraint, the mathematical cost shoots up toward infinity.
Oh, so it acts like an invisible wall.
Exactly, forcing the algorithm to steer the solution back into the safe, feasible region without ever actually crossing the line.
Okay, so the theory is flawless. We have this beautiful engine hunting down negative cycles and dodging constraints with barrier methods. But what happens when this pure math crashes headfirst into messy physical reality?
That is the ultimate test. And for that, we have to look at electronic design automation, or EDA, basically designing physical computer chips.
Right. Min-cost flow is the unified mathematical backbone of modern EDA. It's largely replaced the old greedy heuristics that used to just guess at the best local routing.
Yeah, now they aim for global optimization. So in this context, we take our base network model. The nodes are the routing grid points on the silicon.
And the edges are the microscopic wire segments and the vias, which are the tiny vertical holes that connect different layers of the chip, right?
Exactly. But building the nodes and edges is the easy part. The reality check here is that finding the perfect mathematical flow isn't enough on its own.
Because of the physics.
Right. In industrial EDA, you have to layer on 9 extra categories of physical constraints just to make sure the chip doesn't short circuit, melt, or just fail to compute.
The source lists these out, and it sounds incredibly claustrophobic. I mean, you have timing constraints, meaning the electrical signal has to reach its destination within a maximum delay.
Yep.
You have DRC spacing, which means you have to isolate noisy or sensitive wires so they don't electromagnetically interfere with each other.
You also have to manage via budgets. You have to limit how many vertical jumps a wire can make between layers because every single jump degrades the signal quality.
And you have PDN IR drop, which ensures the power grid doesn't suffer a voltage drop that would cause the transistors to misfire.
It's a lot to manage.
It's insane.
Yeah.
You have millions of wires, and you are basically telling the math, find the shortest path, but don't get too close to that guy, don't jump between layers too much, and make sure you deliver the exact right voltage.
Which leads us directly to the ultimate showdown in the source material. Continuous versus discrete min-cost flow.
Oh, this part was wild.
Understanding the distinction between continuous and discrete math is perhaps the most critical theoretical threshold for anyone working in complex systems optimization.
It's the classic integer programming trap, right? Like
Yep.
continuous math or linear programming lets you allocate 0.8 of a routing track. It's fluid.
Yes, but physical reality demands a discrete choice. You either route a wire there or you don't, a 1 or a 0.
It's like optimizing a supply chain, and the continuous math tells you to ship 2.5 eggs to the store. In a continuous model, that's a super cheap calculation. But trying to actually buy exactly 2.5 eggs at the store, you can't. You have to buy whole eggs, which makes the calculation a total nightmare. Forcing the algorithm to evaluate every single whole egg combination to find the optimal global integer fit causes a combinatorial explosion.
It becomes what we call NP hard. The time it takes to compute scales so aggressively that literally no computer on Earth can solve the discrete problem for an entire modern chip.
So if solving this globally with integers takes longer than the universe has been around, they must be faking it somehow. How on earth do they actually build these computer chips with hundreds of millions of discrete physical wires if the match is impossible to solve?
They use a very clever 4-step industrial solving pipeline. They basically build a bridge between the perfect, incredibly fast continuous math and the messy, slow physical limitations.
Okay, so step 1 is the continuous LP. They run the fast fractional math over the entire chip to optimize global congestion and wire length, right?
Right. This gives them a macro level blueprint, even though it's physically impossible because it uses fractional wires.
Then moving to step 2, they apply Lagrangian decomposition.
Yeah, when you have multiple physical constraints fighting over the exact same wire, say a timing constraint and a spacing constraint, they create mathematical gridlock. Lagrangian decomposition untangles this.
Wait, how does it untangle them? I mean, if two rules are physically mutually exclusive, how does the math resolve that?
By moving the hard constraints out of the physical realm and into the financial realm, so to speak.
The financial realm.
Well, mathematically, it takes a hard constraint, like wires cannot overlap, and moves it into the objective function as a penalty cost.
Oh, I see.
The algorithm is now told, you can overlap these wires, but it will cost you 1 billion penalty points. This decouples the constraints mathematically, allowing the algorithm to find a state that minimizes those massive penalties.
Okay, so we've untangled the mess and we have our highly optimized but still fractional blueprint. Step 3 is greedy rounding.
Yes.
This is where they finally force the fractions into whole numbers. If the continuous math says a wire should use 0.8 of a physical track, greedy rounding snaps it to 1. If it says 0.2, it snaps it to 0.
But rounding blindly like that introduces local conflicts. Wires get snapped too close to one another, or tracks suddenly overlap in reality.
Right, which forces step 4, local integer repair.
Exactly. They take the discrete MCF, the slow, computationally terrifying NP hard math, and they only apply it to tiny localized areas where the rounding caused a violation.
So they don't use the slow math on the whole city. They use the fast math to plan the city, force it into physical streets, and then only use the slow math to fix a few specific traffic jams at individual intersections.
It is a profound compromise. It utilizes the speed of continuous math for the global perspective and isolates the heavy burden of discrete math solely to local fixes.
Okay, so having conquered the microscopic world of computer chips,
Yeah.
how do engineers actually write this code? And how far can this math stretch?
Well, the source highlights a specific toolkit, primarily a package called digraphics. Yeah, digraphics is a prime example of modern optimization tools. It provides a Python front end, which is incredibly user-friendly for defining the network and setting up all the parameters. But under the hood, it compiles to a C++ backend.
So you get the ease of writing Python, but when you hit run, it executes with the raw performance of C++ War.
Which you absolutely need when you are running Howard's algorithm on a graph with millions of nodes.
Right. But where the presentation really stretches the imagination is when it introduces DEC, or discrete exterior calculus.
Oh, this is where it gets really fun. This is where we leave the 1D graphs behind. DEC takes all these 1D network concepts, the flows along lines connecting nodes, and pushes them into higher dimensions.
The source mentions operators with very intimidating names, like the exterior derivative, the Hodge star, and the wedge product. Those sound terrifying. What are they actually doing to the flow?
They do sound like magic spells, but think of them as geometric operators that mutate the math.
Mutated how?
Well, the exterior derivative measures how a property changes across dimensions. For instance, taking the pressure at a single node and calculating the gradient of flow along the edge.
Okay.
The Hodge star is fascinating. It allows you to swap a flow moving along an edge with the flux moving across or perpendicular to it. And the wedge product allows you to combine different flows together.
So wait, by applying these operators, the exact same negative cycle finding engine used to route a microscopic wire on a 1D graph can be mathematically mutated to model flows across 2D surfaces or even 3D volumes.
Yes. Building on that, it means you can use network optimization to solve problems in 3D fluid dynamics, elasticity of materials, or even computer vision.
So what does this all mean for the everyday developer listening to this?
It means that knowledge of network flow is a modern superpower. If you are an engineer or developer and you can look past the surface of a problem and recognize that the complex constraints in front of you are actually just a flow problem in disguise, you instantly unlock a massive library of highly optimized C++ tools to solve it.
You don't have to invent the math from scratch. You just have to realize you are looking at a pipe with water in it.
Exactly. You reframe the problem into the language of nodes and edges, and algorithms like Bellman-Ford or Howard's do the rest.
Okay, let's bring this all together. We started with the basics of network flow, translating impossible logistical combinations into manageable maps using the conservation laws of Telligent's theorem.
Right.
We explored Howard's algorithm and the universal power of hunting down negative cycles to reach perfect efficiency, even when dodging invisible walls created by barrier methods.
We waded through the incredibly demanding physical constraints of computer chip design, balancing the speed of continuous fractions with the harsh reality of discrete physical wires.
Through a four-step industrial pipeline that relies on Lagrangian decomposition to untangle gridlock. And finally, we saw how these 1D concepts expand into multidimensional realms with discrete exterior calculus, mutating from lines on a chip to 3D fluid dynamics.
It's quite the journey.
It really is. So the next time you're faced with an overwhelmingly complex, multivariable problem at work or even in life, maybe stop trying to brute force the puzzle. Take a step back and ask yourself, can I reframe this as a flow problem?
Because if you can define the nodes and the edges, there's a very good chance an algorithm is already waiting to solve it for you.
But before we wrap up, there is one final thought I want to leave you with, building on the source's brief mention of AI optimization.
Oh, this is a big one.
Yeah, we spent a lot of time talking about how discrete min-cost flow, finding the exact ones and zeros for physical wires, is NP hard. It is fundamentally too slow to use on a whole chip.
Right, which is why the chip industry relies on that four-step pipeline.
They rely on compromises, like greedy rounding and local integer repair. It is the only way to physically manufacture chips today. But what happens if artificial intelligence eventually cracks these massive discrete integer problems at a global scale?
Think about the implications of that. What if AI gets so advanced at pattern recognition that it can solve the NP-hard discrete math for the entire chip all at once, bypassing the need for greedy rounding entirely?
If we strip away those mathematical compromises, well, if the blueprint is no longer an approximation that needs to be repaired, but is globally mathematically perfect from the very first calculation, just how much faster, smaller, and cheaper could computer chips become before we hit the literal atomic bounds of physics?
It's a huge question. Are we currently designing our most advanced technology through a blurry lens just because our math is too slow?
It's a looming technological leap that could change the foundation of every electronic device on Earth.
It certainly makes you look at the processor in your smartphone a little differently.
It really does. It turns out that impossibly complex puzzle we talked about at the beginning, we might just be a few negative cycles away from finding the ultimate cheat code.